Okay, video solution for Module 1, Lesson 2. This is the first part of the review. So let's see here. We want to use one or more inequalities to write the intervals on which the function is increasing. If multiple intervals exist, separate them with commas. If the function is nowhere increasing, enter NA. Okay, so first of all, before we jump into these, let's just remind ourselves here that when we're asked to write intervals on which a function is increasing or decreasing, or later on when it's positive valued or negative valued or anything like that, we're talking about parts of the domain. So we want to know intervals of x values where this stuff is happening. The only time that we're going to ask for intervals involving y values is when we explicitly ask for the range. So looking at this function, remember that an increasing function is one that has a positive slope. That's kind of a mathematical definition. We can sometimes talk about this in terms of an ant walking on the function. That would be where an ant walking from negative to positive x value, so from left to right, is walking uphill. So we can see that an ant walking this function walks uphill only between this minimum and that maximum. This minimum appears to have an x value of -3, and the maximum appears to have an x value of +1. We don't care about what the specific y values are. At the actual minimum, the ant is not walking downhill or uphill. That's just the place where he switches between walking downhill and uphill. And at the maximum, he's not walking uphill at that point either. That's a transitional point between uphill and downhill. So it's only at the values of x in between the minimum and the maximum. So that's going to be all values of x greater than -3 and less than +1. Notice that because this interval is bounded on both ends, we need two inequalities to describe the interval. So we would write this as an inequality as x is greater than -3 and less than +1. Okay, where is this function increasing? Well, this function is increasing everywhere up until x equals 5. So an ant walking from an x value of -infinity would walk uphill all the way until he gets to x equals 5, and then from that point forward would walk downhill forever. So this time it's just going to be all values that are less than 5. Now notice that because this interval only has one boundary, it's only bounded on the right, we really only need one inequality to represent it. All we have to say is that the boundary x equals 5 is up until that point it's increasing, and so therefore for all x values less than 5 the function is increasing. We don't need to include any infinities in this at all. It's implied that when we say x is less than 5, that means every value less than 5. Okay, this function is increasing, it looks like, on two separate intervals. As the ant walks from left to right, from off the page, say from -infinity, he's walking uphill until he gets to this peak, or maximum, which has an x value of -5. Then he walks downhill for a short while until he gets to x equals -1. And from that point, he's walking uphill again forever. Keep in mind that we talk about ants, but really mathematically what that means is this is where the slope of the function is positive, is where it's increasing. So because this is two separate intervals, we're going to separate them with a comma, as the instructions say. The left interval only has one boundary. It's bounded at x equals 5. And so we're just going to say all x values less than, -5, not 5. Less than -5, that's one interval on which it's increasing. Let's add a comma and separate the second interval from that. The second interval starts at -1 and increases forever after that. So in this case, because all x values to the right of -1 work, we'd say x is greater than -1. Okay, this is a little tricky. I probably should have added that red line to indicate that this is asymptotic. But this function, as we walk from left to right, even though it appears to flatten out, it never actually becomes completely flat. The ant walking up this function is more and more closely approaching a y value of +1, but never gets there. And so even though he's increasing very, very slowly as he moves to the right, he's still increasing. And so this would be an example where the function is increasing everywhere, and so that interval would be unrestricted. Another way of saying that is all real numbers. But we want to write that as an inequality, and we know that the way to say that the x values are unrestricted is to say that they are all the values greater than -infinity and less than +infinity. Use one or more inequalities to write the intervals on which the function is decreasing. Well, this is really just a flip version of the previous problem. The ant is walking downhill from left to right, and as he walks to the right, he more and more closely approximates or approaches y equals 3, but never gets there. So he's decreasing more and more slowly, but always decreasing. So this answer would be the same as the previous one, so I'll just cut and paste. I'm feeling kind of lazy. Where is this function decreasing? Well, this function is decreasing nowhere because it's always increasing. The ant is never walking downhill. He's always walking uphill from left to right. And so the answer is NA, as the directions state. If it's nowhere decreasing, enter NA. Where is this function decreasing? Okay, this is a restricted function, a restricted domain. And we can see that the ant is going to be walking downhill from his left endpoint all the way down to the minimum or the valley of the function. And from that point, he's going to walk uphill. Okay, so as we said before, he's not decreasing at the minimum. That's the place where he transitions from decreasing to increasing, so we won't include that x value of -1. And also we can see that the left endpoint is not included. So the x values that we would include would be all values greater than -5 and less than +1. Okay, this function is decreasing on multiple intervals. The ant, as he walks in from the left, from infinitely far to the left, he's going to be walking downhill the whole time until he gets to an x value of -3. He's going to transition and walk uphill until he gets to x equals 0, and then walk downhill again. And so for us, we're going to say that the left interval only has one boundary. It's bounded at its upper limit of -3, and we're going to keep all the x values to the left of that. So all we have to say is x is less than -3, comma, which stands for or. X is greater than 0. Those are the two places on those intervals the ant is walking downhill from left to right. So therefore the function is decreasing. Okay, now we're going to switch gears here a little bit. We want to look for where the function is positive valued. A function, when we say a function is positive valued, whenever we refer to the value of a function, we're talking about the y value, of course. And we know that y values are positive whenever the function is above the x-axis. So visually, we're just looking on the graph for all the places where the function is above the x-axis. We can see that the function is above the x-axis everywhere to the left of this point, which is at x equals 2, and between the x values of 5 and 8. So then we would say that either x is less than 2. And I should mention, why don't we include 2? Well, at 2, that's a 0 of the function, or an x-intercept. At that point, the function has a y value of 0, and 0 is not positive. So we can only include the values up to, but not including 2. So x is less than 2, or x is greater than 5 and less than 8. This function is positive valued, it looks like, using similar logic between x equals -6 and x equals 1. So there's one interval. Oops. X is greater than -6 and, whoops, less than -1. Or, looks like the function's negative value, the ant's below the x-axis for a while, and then at x equals 8, is where he crosses the x-axis, and for all values greater than 8, all x values greater than 8, he's above the x-axis, and so the function is also positive valued there. X is greater than 8. Last one. Positive valued. In this case, there are 2 intervals where the function is above the x-axis. All values, x values to the left of 4. If we move to the left of 4, notice that the function is above the x-axis. If we move to the right of 7, the function is also above the x-axis. For all values between 4 and 7, the function is below the x-axis. So we're only going to include the left and right intervals here. So we'd say x is less than 4, or x is greater than 7. All right, that's it.